Earlier, we stated that when a magnet is cut in half, and those pieces are cut in half, and this is continued all the way down to the atomic level, then each piece would still have a north and a south pole. It is now time to explain why this happens. The real explanation requires an understanding of quantum mechanics, but we can use some classical concepts to give you a working understanding of the cause. What's very nice is that the classical Bohr model leads into the quantum mechanical explanation. Classically, the Bohr model of the atom shows electrons orbiting the nucleus, just like the solar system, planets going around the sun. Current, which is made up of moving electrons, generates a magnetic field, the strength and direction of which is called the magnetic moment. Another contribution to the magnetic field of the atom is a thing called electron spin. Since the electron is a point particle, it really isn't spinning at all. But this is a term created and explained by quantum mechanics. This spin factor adds to the strength and magnetic field created by the orbital motion of the electrons. So each atom acts as a magnet with a north and a south pole, and the key word there is it acts like that. We have another term, the magnetic dipole moment, and the magnetic dipole moment of an electron is pointed in the opposite direction of the angular momentum of the electron as it orbits the nucleus. And of course, we're still talking about the classical model of the atom right now. This magnetic moment is a measure how strongly it will interact with an external magnetic field. Using the Bohr model, we have an electron traveling clockwise this way. But remember, our conventional current is opposite the electron's motion, so it goes like this. So when you use the right-hand grip rule, you'll get a magnetic field or the magnetic moment in that direction. The angular momentum is down this way because that depends on the physical motion of the charge. It doesn't care whether it's positive or negative. And mu, this is our symbol for magnetic moment, and that represents both the direction and the strength of the magnetic moment. So obviously when we're doing the direction, we need the vector sign. The arrows in the below diagrams represent a bunch of atoms and their magnetic moments, with the arrowhead the north pole and the other head the south pole. So here's a group where all the magnetic moments are in the same direction. Here's another group. This one you can see more of them are in the same direction, and this they're all aligned. Each group of like-pointed arrows is called a magnetic domain. In a magnetic domain, each atom has its magnetic moment in the same direction, just like we circled down below. What do you think is happening? Which picture could be a permanent magnet? Which could be a piece of plastic? And remember the definition of magnetic moment. It tells you how strongly the material interacts with an external magnetic field. For a group of most atoms, there is no real reason for the magnetic poles to align. The picture on the left shows a pretty random ordering of magnetic field directions, with aligned fields only in each magnetic domain. Looking at the left picture as a whole, the various magnetic fields cancel out, so it would not be a very good magnet in this state. It could be a piece of plastic, or, and we'll get to this shortly, a certain type of metal that could become a magnet with the application of an external magnetic field. As you move from left to right, more of the magnetic field lines are in the same direction. For example, in the middle here, you have a large domain where all the field arrows are pointing up. Finally, in the third picture, all of the field lines point up, and you could visualize it as a bar magnet with the north pole facing up. When you apply an external magnetic field to materials, they respond in three ways. Ferromagnetic, these materials can be permanently magnetized by the application of the field. All of their domains will line up in the same direction. Examples: iron, nickel, and cobalt. Paramagnetic, the material weakly interacts with the external field and temporarily lines up some of their domains so they're attracted to magnets. When the field is removed, the domains resume their random ordering. You have magnesium and lithium. Then finally diamagnetic, which is another weak temporary effect, but in this case, the domains line up opposite the external field, so they are repelled by a magnet. Examples would be bismuth and antimony. These diagrams show the alignment of the magnetic domains in the presence of an external magnetic field, B. So we've got the external magnetic field pointing in the up direction. Paramagnetic materials, some of the domains will line up with the magnetic field. Diamagnetic, some of them will line up opposite the magnetic field. See how the domain arrows are pointing down? And then ferromagnetic, all of them will line up with the applied external magnetic field.